we've kind of teased this now a little bit, and thrown this term around, graphene and nanomaterials and stuff. So let's break that down first, because I was shocked when we first chatted about where graphene comes from and just this idea of nanomaterial. So maybe you could define nanomaterial and use the example of graphene, where it comes from, how it's made, and what makes it a nanomaterial, and why nanomaterials are so interesting.
Well, actually, there is actually like a definition for nanomaterials, so it isn't kind of like a wishy-washy thing that we kind of just go like, oh, that one's a nanomaterial, and I don't like this one, so I'm not going to say it's a nanomaterial.
Okay.
So it's just that one of the dimensions of a material needs to be less than 100 nanometers, and
All right.
that's essentially it. So it's just you imagine that you take like a block, and if you just decrease maybe its height down to being 1 nanometer or less than 100 nanometers, then it would then technically be a nanomaterial. And that's essentially what graphene is. Graphene is just a sheet, a very,
Right.
very thin sheet of atoms. But yeah, it comes from graphite. So graphite is like a deck of cards when you look at it under a microscope, but each one of those individual playing cards is a sheet of graphene. And then we kind of then use chemistry and stuff to then break apart this deck of cards into the individualized sheets. And then we can then kind of play around with them and use them. And generally, we do this in kind of liquids. An issue when graphene was discovered is that people literally got tape, put it on top of graphite, and then started to just peel off the layers. And that
And
was an issue.
graphite is just like pencil lead,
Yeah, it's
right?
just pencil lead. Yeah. So it's just essentially your pencil lead. And we've shown as well, like in a paper that we did a couple of months ago, is that you can literally take pencil lead and you can turn it into graphene, and really, really good graphene that's similar to the stuff that you make from, going to a commercial supplier, specifically buying graphite that's been milled up and everything to then use in labs, is that you can take any old graphite and then turn it into this kind of wondrous material.
Right. So to make a nanomaterial, it's got to be really thin, and it's usually these thin sheets. That's how we think of it, right? Is like these
Yeah,
these
so we
thin
have these
sheets of.
nanosheets, and then also you can have the kind of tubular shapes. Is that you kind of decrease another dimension, and you essentially make this elongated array of atoms. Is one of kind of the other forms of graphene as well. That you can take a graphene sheet and essentially have it rolled up to form a tube, and that's the carbon nanotube. A carbon
Hmm.
nanotube is just a graphene sheet just rolled up, or a graphene sheet is a debundled or kind of a unscrolled nanotube material. So they're just all what we'd call in chemistry like allotropes of carbon. It's just the different forms in which carbon kind of form together. But graphene isn't kind of the only nanomaterial out there, or the only atom that kind of or element that forms nanomaterials. We have a whole zoo of them. So we have boron nitride, which is boron and nitrogen atoms similar to graphene that just kind of just sits in a sheet, and it's an electrical insulator. And then you have something called molybdenum disulfide, which is molybdenum and sulfur atoms again in this kind of just planar sheet form. And then that's a semiconductor. And right there, you have kind of the basis of kind of your basic computing is you have graphene, a conductor, you have a semiconductor, and then you have an insulator. And then that's where you can go and kind of start making electronic devices then.
So then, when you break, you got graphite, which is boring pencil lead. You put it into this graphene form, this really thin thing, and it gets like new properties or enhanced properties. How would you describe that?
We
And
we would say that it kind of like, yeah, that it like enhances it, it optimizes the properties, and which is why it kind of why nanomaterials are so exciting. Is that if you look at graphite, we all know from kind of with a pencil, you're writing and it's very brittle. You're constantly having to sharpen it, so it's not very very strong. And then also then if you take graphite, it's not a very it conducts electricity, but it's not an amazing conductor of electricity. But when you then optimize it by breaking it apart into the graphene nanosheets. Graphene is one of the strongest materials that we know because it's based on trying to break molecular bonds in the actual sheet rather than with graphite. It's all these sheets sitting on top of each other. So when you start to then try and pull it apart, it's just the sheets coming apart rather than actually pulling the actual graphene sheets. And then also as well, graphene is an amazing conductor of electricity and heat. because it's just this single sheet, so the electrons can just zoom across the surface. Rather than in graphite, it's all this muddled amorphous structure. So all the sheets are all crumpled up and they're all smushed together. So to go from A to B across the graphite, it's going to go like up and down, and oh, I have to go backwards and forwards and everything. So yeah, it's essentially it's just optimizing the properties when you what we would say exfoliate these kind of layered materials down to their kind of nano form. And it's the same with, molybdenum disulfide as well, is that when you kind of start to strip away its layers and get down to the single layers, you actually are able to kind of tune the band gap of the material as well and tune its properties to make it more advantageous for electronics. Because in the bulk as well, molybdenum disulfide, it isn't used for anything in electronics. It's actually just used for a lubricant most of the time. It's actually a very, very good mechanical or solid state lubricant. So you literally just get the rock and you kind of rub it around the joint and all the layers come off and they just form this kind of just slippy layer that you can then kind of just put two metals together and they'll be able to form some type of actuation where you kind of have the mechanical gears going. So it's essentially you're just discovering all these amazing properties from these materials by just kind of turning them into nano. And it's the same with, looping around to our Mars study as well, is that we just took kind of boring rocks that people more or less assumed had, not very interesting properties. And when we exfoliated them down to then kind of their nano form or into these kind of nanorods, is that we found that they actually turned into semiconducting materials and they had these very interesting properties and they could, have the clean energy harvesting and, we could use them to kind of reinforce polymers. So it's just like, this is what's kind of very exciting about nanoscience is that it's like that unknown. It does seem like a little bit, I suppose, what I say kind of repetitive because you can just keep on going, well, let's just get that material and try and see if we can turn it into a nano sheet or a nanotube, and let's get that one and let's get that one. But the thing is that it is cutting edge science because we simply don't know what's going to happen to these materials when they go down to the nanoscale, and that's when all those kind of crazy properties come out.
Okay. So that was kind of what one of the other questions I had was, can you sort of predict what material, when broken down to a nano level, will have interesting properties? But before I get there, it's like, do all the nanomaterials, is it all just about sort of stripping away the sort of resistance is maybe the wrong word, or the clutter, right? And so when you get down to like those sort of atom level, thinness, you just, like you said, electrons can move much faster. It's stronger because you're actually trying to break the bonds and not just this brittle layer of stuff. So is it
Yeah.
really just like, is that sort of the core of what makes nanomaterials, or is there other sort of, sometimes I think about it, I could be way off, that it's like, when you get down to the quantum level of things, like there's this weirdness that we don't
But
understand. So is
that
there something
that
that we don't?
It's yeah, it's a lot of the quantum effects that start to kind of come into play when you start to go down to those very, very small dimensions, and you start to have all these kind of funky effects that occur. I won't go into because I don't want to go into like a huge amount of kind of physicsy stuff. But I mean, like, yeah, that a lot of it is to do the going down to these kind of quantum levels when you start essentially you almost have like a macroscopic material that's then being confined down into these kind of quantum realms, and it's that kind of combination where you kind of get these really, really interesting properties. But to go to your point of kind of being like, oh, can we kind of predict what a material might do? Is that not all materials can kind of be broken down into some type of, I suppose, nanomaterial. Like I mean, for kind of bricks and mortar and things like that, like they won't necessarily form some type of structure like graphene, like a sheet, or that they won't form these kind of nice tubular shapes or anything, nothing
Oh,
kind of
okay.
uniform. So it has to kind of really depend on kind of the actual physical structure and the lattice makeup of the material to use kind of a physicsy word, like how the atoms kind of arrange together, for us to be able to kind of go like you can see physically where you could kind of strip down the materials. Because I mean, going back to graphite, is that you can see the layers in
Right.
graphite. So you can kind of see, okay, so this is what's going to happen when we try and use these exfoliation regimes. It's going to peel off these layers. We're going to get some thick layers. And if we keep on this peeling process, eventually we're going to get down to a single layer. And then if we keep going, we're going to then start to tear up these kind of smaller layers and, being able to kind of control size and stuff.